Sean T. Allen. If you're going to tweet about this or anything, the T is really important. Please make sure that's in there. Years ago, before I started using the T, if you were to search for me on Google, you'd end up with a real estate agent in Arizona, not me. A while after that, you started getting a guy who'd been arrested for dealing crystal meth in North Carolina, also not me. And if you just search for Sean Allen without the T now, still not really me. So remember the T, it's important. So a little bit about me before we get started. I'm one of the authors of a book on Apache Storm called Storm Applied. I'm a member of the Pony core team. Pony is a high-performance actor-based language. I'm also the VP of engineering at Sendence. We're a startup based out of New York City. And really today, this is an experience report for how we've gone about getting confidence in the system that we're building. If any of you saw Ben's talk this morning, what we're building is a stateful stream processor. Originally, it was called Buffy, but we're getting close to the time now when we'd be releasing it. And so, we didn't want to have Josh Whedon's lawyers come around and get on us. So instead, we've named it Wallaroo, which is nice because you get cute little animals to go along with it. And in keeping with our general Buffy theme, there's still like demons that look a little bit like Wallaroos, so that's not bad. But with that change, we've still kept our general naming theme for it, which is that every component of the system has to be named after characters from Buffy the Vampire Slayer. So if you're familiar with Buffy the Vampire Slayer, you can get reacquainted with a lot of your favorite characters in different ways, but not Willow, because we haven't had anything that's cool enough to be called Willow yet. For the system that we were building, we started in January 2016 with a prototype that we did in Python, and we have a production version coming out next month, basically, which is written in Pony. And in the end, we're really about creating a system that has really high performance. Our goals going to this were to have really high throughput, really low latency with flat tails, running on a lot less hardware. To give a general idea about that, when I run it on my 2014 MacBook Pro, we get some pretty good performance, like 220,000 events a second without really pushing it, doing like 99.99% are processed in 500 microseconds or less. And there's an awful lot of work that goes into that, and we end up changing the code an awful lot. So a lot of this talk is about how are we feeling comfortable making all of these changes that we do and knowing that we don't break the guarantees in the system, because the other big part of this is what we really have is we have this idea of we want to be a high fidelity system. That is, we are a stateful stream processor, and by being a stateful stream processor, that means that we're keeping in-memory state for any particular calculations that would be going on within the system. And in the face of failure, we want to know that we're actually giving correct results, because effectively we are some sort of simplified version of a database in a lot of ways, and you want your database to give you correct results even in the face of failure. How many people here are actually familiar with stream processing? Okay, good. Well, I'm going to give a little bit of a quick run through for people who aren't. Stream processing generally is a way of dealing with data where you handle like a message at a time, events as they happen, they come in, and you process them. It's a never-ending stream, just right on through. And when I talk about failure through this, like what kind of failures are we talking about? They could be machine failures. Could be a slow machine. This machine can get slow enough that it's effectively a failure. Seg-faulting processes, GC pauses, network errors, whatever it might be, there are failures that happen. And in stream processors, generally, when you have failures, you have some type of delivery guarantees for what you're going to do if any sort of failure happens. In general, there are a couple different ones for that. One of them is at most once. This is basically a best effort thing where, hey, I tried to deliver that to you, you didn't get it, I'm not going to send it again. I made my best effort right there, but there you go. A stronger guarantee there would be at least once. This is basically where, hey, I send it to you and you need to acknowledge it. If I don't get an acknowledgement within some period of time, I'm going to go ahead and resend it to you. And then the holy grail for most stuff is what's called exactly once, which in general, when people say exactly once, what they're really talking about is you have at least one semantics where you're going to keep resending stuff, and then you have some sort of idempotence on the other side, so that if you end up getting duplicates, it's fine, it's okay, they'll go ahead and they'll be filtered out and you still get the results. So the exactly once part, it's really important. Within our system, we guarantee exactly once semantics for processing of data. What this really means, if you take a really simplistic case of like, if you have a counter and you have messages which are going to come in and tell you what you're going to do with this counter for like adding and subtracting from it. If our counter starts at 0 and we go ahead and we have message 1 comes in that says add 1, we go ahead, we increment to 1. If we have message 2 comes in, you know, it says, hey, add 5, good, we go ahead, get 6. If we get a duplicate here where we have message 1 again, right, then we're not actually going to add to it, we just keep the value of 6. And in the end, that's really basically what at least once with idempotence is, all right? And that's a guarantee that we want to have in our system. So really, the core of this talk is it's not about our product. It's about how we go about feeling confident as we're doing a lot of changes in order to get better performance, and be that, you know, in terms of throughput, latency, memory uses, et cetera, that in what is a reasonably complicated system, that we haven't broken any of these guarantees, right? And so really, this in the end, this is a talk about black box testing, and in the background faded out there a little is a picture of Peter Alvaro, who wrote a paper about lineage-driven fault injection, and this talk is really my love poem to Peter, because I love lineage-driven fault detection. So let's start with talking about black box testing and what that is, if you aren't familiar with it. Basically what we have is you have a system that's under test, and you have some input source, which sends data into that, and you have something which goes ahead and it receives that output. In our particular case, what we have is Wallaroo, that's the system under test, and we have an input source which is called Giles Sender, which goes ahead and sends it in, and we have Giles Receiver on the backside, which receives the data. And one of the big reasons why we do black box testing is because unit tests aren't enough for this. We can go ahead and we can have all of the unit tests that we possibly have. They can pass, and our system can still be completely and utterly broken. Integration tests are nice, but they aren't enough either, because in the end, you know, in general, this is usually happy path testing, and we have a lot of different components that when you start composing together, you get all sorts of interesting new failure scenarios. If you have the time and inclination at some point, there's some really interesting Kafka bugs that used to happen earlier on when different parts of Kafka, which had all been independently tested and proven to be correct, when you actually put them together, had strange emergent new behavior where stuff just didn't work. So even if you've proven each individual component works, you don't actually know that your entire system works. So we're big fans of black box testing. We test the entire system, we test it end to end, and we verify that it's actually meeting our expectations and what we said it was going to do. So a primary part of this is Wesley. Wesley is our expectation verification stuff. Ooh, and I forgot to change Buffy on there. I thought I'd gotten all of those. Oh well. So basically what Wesley does, if you imagine our black box is a thing which takes in integers and it's going to go ahead and double them, and we have input here which is going to be like 1, then 2, then 3, and we're going to have some output that we expect for this, which is going to be 2, 4, and 6. An important part of this is we have to know, based on what the black box is, what our expected output data is based on the input, and we'll get into this more later, because when you have non-trivial things that you're talking about, this gets to be one of the really hard parts of it. So in our case, right, we have our input source, which comes from Giles Sender. We have our output receiver, which is the Giles Receiver, and our input source sends like 1, 2, 3, 4, and we expect to see 2, 4, 6, 8 coming out the backside. So what we have in this case, right, is this is a fairly simplistic one where we have guaranteed ordering on this, and we have We have our input, we expect it to match up to our output. What we do is we go ahead and we have Wesley, and we tell it to analyze. So what it basically does in a simplified form is, it looks and goes, hey, okay, the first entry was 1, we expect to see 2, et cetera, on down the line, right? And hey, all right, awesome, it works. It's a simple, basic test right there. And in the end, though, for this, that's a happy path test in the end. There are no failures there. If that doesn't work, then we have some even larger problem. So we have another system. This is called Spike, and Spike does fault injection. So, and this is really the big core of the talk. So fault injection, and in particular, we practice a form called linear-driven fault injection. Fault injection is when you go ahead and you intentionally introduce errors into your system. This can be a really huge problem space, and lineage-driven fault injection helps you narrow down your choices of faults that you're going to do. And it seems really, really simple for an idea, but it's one that until I read the lineage-driven fault detection paper, I hadn't really thought about this is a way to do it. So the basic process is you start from a known good result that you're going to have, where you expect if you send in 1, 2, 3, that we're going to get 2, 4, 6. Then we go ahead and we look at this and go, what could go wrong? What could go wrong inside of that black box that could cause us to get incorrect failures? And each of these things that you come up with is a nemesis. So in our case, we started because we're a distributed stream processor, but you could do this for any other system, coming up with different things. We started with the network is going to be our first thing. And we have a number of nemesis, but I'm just going to talk about the network one here, because in the end, this is about how could you go about doing this yourself. So we have the network, and one of the key things that's really important here is you have to have determinism here. If you can run the same test over and over again with the same fault being injected and you get different results, then it's completely useless. It's not going to help you at all. And getting that determinism is one of the hardest parts of doing this, even just with network stuff. So in our system, we basically have our nodes communicating with each other over TCP at this point in time. And what we do is we go ahead and we inject failures based on TCP and the guarantees that TCP makes. And it makes a number of nice guarantees for us. For example, it says that between any point-to-point communication, that delivery is guaranteed to happen in order. If I send message 1, then message 2, it's going to arrive as message 1, message 2. It's not going to get reordered. So we're depending on that. It also guarantees that if, at the packet level, there's any packet loss, that it will go ahead and resend, and it will do deduplication for us at the network level. Then, additionally, like I said, it will retransmit any lost data. So now we are building this stuff in Pony. So we're going to dive in a little and look at how Pony does network stuff, because this becomes very much you have to hook into how your system works in order to do fault injection. So what basically Pony does at a network level is it's event-driven, so that when, for example, you have a connection that's established, you have some code over here for a callback. It's called connected, that happens when that connection is established, when there's incoming data, the callback for received happens, etc. So the callback classes that you write for this, they're called notifiers. This is a really simple, useless notifier here. Right here, you'll see this is the notification for what happens when connected is called. In this case, it doesn't do anything other than print a standard out that, hey, this connection was opened, and when the connection is closed, hey, the connection was closed. So the first one that we wanted to go about testing was what happens with drop connections. Basically like network partitions, et cetera. They happen, et cetera. So we came up with a bit of Spike, and this is a segment of it for dropping connections. So what we have here is we have a little bit of it. And what we went ahead and did in this particular case is we wrapped our normal code, the normal notifier that we have up there, the letter, and we went ahead and we wrapped that with the spike one, and then at the time that the application starts up, you can either choose that you're doing a fault injection run where we put in all the spike ones where they can be run, or you don't, and then we don't put them in, basic dependency injection stuff there. And then we also have, along with it, we have the dice object is a random number generator, and we have the probability of an event happening. So in general, basically what we have is, so you go ahead and we have our received one here, and the basic way any of these work is we go ahead and we check to see, are we supposed to spike this? If we are, in this case it's a drop connection one, so we go ahead and drop the connection. And if not, we just go ahead and we do the processing as it would normally go. And for the spike logic, what we basically have is we roll the dice, and if it's less than our probability, we're going to go ahead and we're going to drop that. Now, the important part to go along with that, is that this needs to be deterministic, so we need to be able to set specific seeds for this, and we want it to happen so that if we use seed 1, 2, 3, that whatever happens on any run for 1, 2, 3 with a given input set, we're always going to get the same result. Otherwise, we'd be chasing our tails forever trying to figure out what's going on. So, in general, these are all different places where we ended up introducing drop connection. Like, hey, when an incoming connection is first accepted, we might not even get through a full handshake. We could potentially have it happen then. When we're attempting to create outgoing connections, we could also have it drop then. When the connection is actually established, when data gets sent, when data is received, any of those, we go ahead and we introduce it at any of those points. And the basic way that we go about doing this is we follow what in general sort of looks like TDD. And we go ahead and we take, in this particular case we had, this was a very popular one for us in the beginning, was a simple app called Double and Have, because it's really easy to look at the results for this and know that it's correct. Because if you get 1 going in, and it goes through double, and you don't go to 2, and then we send it off to a second node where it's going to have it, then we expect to get like 1 back out the outside. And the Wesley tests are really easy because this is just identity. And if it goes 1, 2, 3 in, it goes 1, 2, 3 out. It's a good place to start. So, all right. So what we go ahead then, same thing with 2, et cetera. You get the idea. Easy to verify. Another reason why we do this is that we can do this as a simple one where it's 2 steps, and we're going to be processing process boundaries, and by doing that, we're going to cross network boundaries for that. So the way we do this first is we do the double and have, and we go ahead, and the first thing we do is that we run it without spiking, because, hey, well, we need to know that it actually works in the first place. If we have a broken thing in the beginning, then we could just be chasing our tails. And we test. We have CI, et cetera, for this. Hey, every time somebody commits, it goes ahead and it does a normal regular run. And if everything passes, awesome. Then we go ahead, we take the same app, and we start turning on drop connection, and we test it. And for each one of these, it better fail. If it doesn't fail in the beginning, then we have a problem, because we have something that we didn't do right. If that doesn't fail, then we probably implemented something about the spike component itself wrong. And that's a big part of it, is that you need to be able to guarantee that your fault injection code is actually introducing the faults that you expect. So we go ahead, we do it. Hey, here we go. It breaks. We got to fix it, right? And in this particular case, fixing meant, we needed to have session recovery where we've lost a TCP connection. We need to reestablish that connection, right? So we came up with our wonderful session recovery algorithm. It's not actually ours, like it's a standard one that most people use. And you do the same thing again where we go through after that's been in there and we test it, and it should pass. And like I said, we need to be able to do repeated runs, and if we get different results, then this is pretty useless. We're not going to be able to do anything with it. On the determinism front, this is actually really easy to get wrong, and we actually got this one wrong multiple times before we got it right. Part of that is that TCP is not deterministic in terms of how things are going to arrive. There could be any kind of delay in between when stuff shows up at the network card. We do get the delivery order guaranteed. That's great. We still get the duplicate detection, et cetera. We're not going to lose data, but there's no determinism in terms of when the stuff is going to arrive. Like if we have 100 bytes of data that we're sending from one machine to another, it could arrive in a grouping of 50 bytes and another group of 50 bytes, or it could arrive like, 20, 30, and then 25, 25. And so what we had originally done was we were spiking our individual received calls, and that didn't work. And once we saw it didn't work, we were like, oh yes, that's obvious, because one time this could be called with 25, another time this could be called with 50, and we're going to get these different results. So what we did is we introduced this idea of expect, which is basically you can tell like a connection, hey, don't call the received method until you get X amount of data. And in this particular case, we're using a framed protocol, so we can know how much data is supposed to come in. So if you're not familiar with what a framed protocol is, it's basically something like this, where you have a header of some size, right? 4 bytes here in this particular case, which is going to tell you like what this payload is that's right here, right? So in this particular case, we have our header, which says 18, and that means that our payload for the next one is going to be 18, right? And we get 20, the same type thing. And so basically how this works is you go ahead, and when you're inside of received for this, what you want to do is you want to say, hey, I'm going to go ahead and I'm going to read off these bytes here, right? And this is going to get my expect value because I'm in the header. In this particular case, this should give us 18. And you're going to go ahead and you're going to say, OK, I'm now expecting 18 bytes for a payload, and also I'm no longer in the header. And then we can go ahead, and once we're not in the header code anymore, we can do our standard, we run it through a decoder for whatever our particular payload is to turn it into whatever. And you can see here, all right, OK, that matches up with our 18. And then when we're done with that, we know that we need to expect another 4-byte header, and so we go ahead and do that, right? And so it'd be 20. So what it means is that when we get 100 bytes, and no matter how it comes in, any of these things, we're always going to get this. We're always going to have our method called with 4, then 18, and then another 4, and in this particular case, 20, right? Same number of notifier method calls, no matter how the data arrives, and now we have determinism again. Seems remarkably simple, but we messed it up the first time. That was one of those, wait, what's going on here? So, yep, drop connection and expect fast deterministic friends. We did another one, which is for slow connections. This was a fun, interesting one as well. How do you go ahead and simulate a slow connection if you want to put it in? So what we did in this particular case is we go ahead, and this is our delay receiver right here, right? And what we do is in this particular case, we actually override expect here, where we go ahead and the notifier that we're actually wrapping, what we have to do is we have to call its expect before we do anything. And we go ahead and we get how much it's actually expecting based on its given state, because when we're wrapping it, you can't know, like, it could be a frame protocol, it could be a fixed width protocol, we don't know. And then we go ahead and we return 0, and what 0 means is just give me all the data that you have available, right? So we go ahead and we override that, and then our actual delay one here can control the flow of bytes. It's basically acting then again as another layer in between to maintain the determinism. So this actually took us a while to get right. We did multiple attempts at this, and each one of them had slight little things that were wrong with it. But basically what it is we had to set up a minimum and maximum number of bytes that we go ahead and allow through, and a minimum and maximum number of bytes that we would go ahead and delay. Then we use a seed, and the seed, well, when we're in either a allow data through or a delay period, it will go ahead and the seed will pick something in that range of this is how much to expect. So for any given seed, you'd have it, but it's not always going to be 500 bytes that we allow through, then 100 we buffer or whatever. There's some randomness in there to try and determine edge cases. So if you'd have something like, hey, okay, we got this, we got some input, and it's going to go ahead and it does the random stuff, and it'll come up with, say, all right, I'm going to allow 800 bytes to go through. Then, I'm going to go ahead and I'm going to buffer 400 bytes before we go ahead and we send anything else through. So, you know, if we get 1,000 bytes that come in, we're going to go ahead and we'll take 800 of them and we'll send them through immediately, and we still have 200 bytes that we're buffering. We're supposed to buffer 400, so we're going to continue buffering those 200, and we're going to delay until we get another 400 that comes in, which means we can then start delivering stuff again. So what do we find from this? Well, when we actually implemented this, everything seemed to be working fine for a while, but then like maybe 1 out of every 50 times or so, we'd see some weird error where we weren't actually getting the results that we were expecting coming back from Wesley tests. And it took a long time for us to figure it out, but we actually found that we had a bug in the session recovery where it was making certain assumptions about like the IDs that were being used to communicate back and forth across the channel, which were incorrect. Those are always fun. It's one of those ones where you're like, hey, we're trying to get a product out the door. We did the thing. There was even a little to-do next to it that said, this might not be right. We should probably come back and look at that later. The infamous to-dos, which, you know, oh, those are always so fun. We also found bugs in the Pony standard library. That was a fun one. And we also found bugs in the spike implementation. I wrote the drop connection spike implementation one, and our first thing we had to get past was that we actually had bugs in how it was doing it. And the code that I actually showed you earlier, I left it in there. The bug is actually in that code. Feel free if you ever wanted to go back and look at the slides and see if you can figure out where the bug is. I stared at it for about an hour and a half before I realized what was going on. But it's a fun one there. And, you know, we found still more bugs. And, you know, in the end, you know, what this really about is that determinism was the key. The spike bug that we actually had, that was the worst one of them all because it was messing up the determinism and we weren't getting the same runs through each time through. It was causing real problems. And so, like, that's one of the first things. If you decide to go about doing something like this, whatever you're using for fault injection, you need to come up with a good way to test that you're actually getting determinism from your fault injectors. And we didn't do it in the beginning, but now, like, the first big thing that we really do, in the beginning we were like in a real rush, and we're like, yay, we're really excited to do this. So we'd write the fault injectors, we'd stick them in, and, you know, we had the good run, and then we turn it on, and we just expected the fault injector itself to work, and we're testing everything else, and we're somehow magic programmers who can write fault injectors without introducing bugs into them. But, you know, that wasn't the case, so we spend a lot more time now, and, like, the biggest area that we have for unit tests in our code base are actually the fault injectors themselves, because those are really hard once you turn on, like, the tests for the entire system. You can end up chasing ghosts for a long time if you have bugs in the fault injectors, and you know, but if you have, they're usually relatively easy to find if you have unit tests for them. It's one of the areas where I very much love unit tests. So I want to talk a little about data lineage. This is something that we're looking at and we think is really important overall when you're doing fault injection type stuff. This is another thing from Peter Alvaro. We're looking at introducing it into ours, but we haven't yet. It's just something that we've thought about. So this is far less thought out, but if this is something that you're looking at, wanting to take on or whatever, this is, you know, definitely something where I think go ahead and check out data lineage. So the basic idea for data lineage is you have some set of outputs, 2, 4, 6, and you want to know how did we end up getting to 2, 4, and 6, right? So if we have some input, 1, 2, and 3, right? And we expected 2, 4, and 6, but we got 4 and 6. This is great. It's wonderful. But, you know, how did we get there? Those are not the results that we were expecting, you know? By the same token, 1, 2, and 3, we get something else here, and it's entirely different. It's still wrong. Who knows? It's great. The test found the problem for us. It pointed out to us in a nice automated fashion that we're doing something wrong, but we have to go in, and the way that we do it currently right now is anytime there's a failing test, we store the seeds in the input set that we used in order to do this, and we go ahead and we have to step through it and figure it out. And what we'd really like to be able to do is be able to dump out the data lineage and be able to, like, store what actually happened in this particular case. And that would end up saving us a lot of time. And in a lot of ways, really, what it's doing is it's going to verify, like, do we have determinism, right? And in our particular case, it's really about finding incorrect, like, executions. Like, if we have something like that happen, then in all likelihood, we have something wrong in the core part of our product where you've given us a couple different computations, right? And we go ahead and strung them together wrong. So you could take where it's something like this, right, where we accidentally routed this through double 2 times when what we meant to do was route it through half, right? And if we go ahead and we have the lineage and we know that each step along the way, right, this went from double to double, then when we have that along with the failing test result, we can look at that and go, oh, well, this was supposed to do double to half, so we have some problem in how we're going ahead and we're setting up these topologies for people. I mean, these are fairly basic things, but we've actually had a couple of cases where we had ones where in code paths that get executed less often, we'd accidentally done this. I think my favorite one was the one that we were looking at for a while, was we had a crashing bug, which really would have been helpful if we had this, because it turned out that we had a slight bug, which type checked. We strongly typed language, love types, but type checking couldn't help us when we accidentally, in one part of the bug, connected. We have 2 paths. We have the data path that everything goes down, and we have a control channel for nodes to communicate back and forth between each other to say things like, hey, I exist, I'm part of this cluster now. And what we did was we accidentally had it so that the control path from nodes which were only talking to ones that were downstream from them, they only had external input sources, were actually wrapping their control panel back around and attaching to their incoming source and sending weird junk back down in. It was, of course, it was a 1-character bug, as these things always are, and it took us about 6 hours to figure it out. It would have been really nice if we'd had the data lineage there to show us, like, where did this actually come from beforehand. This is not a particularly new thing in being able to follow these. Like Google has, like, Dapper, for example. What's the Twitter one? Is it Zipkin? Zipkin, that's right, yeah. I mean, so these ones where you can go ahead and you can trace stuff through a system. It'd be really awesome to have. It's also useful outside of development. I really wish in all the times that I was running Storm clusters at my last job, that we'd had something like that for production debugging. I can't remember the number of times I was up at 3 o'clock in the morning trying to figure out why the jobs which were essential to the business running and making money the next day that needed to be done by 6 a.m. were failing and had been for 3 or 4 hours, and you're looking at log files that just spew out hundreds of thousands of lines in a few seconds, So that would be really awesome to have. It would also be great to be able to go back through later on to have, like, a data lineage system and something where you could get an audit log and you can say, hey, why did you do that? We're targeting, like, finance as our primary space, and even though we say, hey, this is vaporware and might have a real serious impact on the performance that we're going for, like, lots of banks look at that and go, ooh, wait, so you mean I can tell the regulators why we made a decision based on what the state of the world is at the time? So, I mean, there's a lot of value for it. From that, it's basically a big, giant, wonderful hindsight machine, which is, yeah, love it. So, if you take one thing away from this, it's that, building confidence in these types of systems it's really difficult, and I think this was me most of the time. It was really frustrating, but in the end, it's worth it. Like, we're getting ready to, like, put stuff out into a POC with, like, a large client where, if it doesn't work on those most basic levels, then we've basically sunk a potential, multi-million-dollar project with people, and we'd never probably be able to get another chance with them ever again. And there are only so many really large banks in this world. So we really don't want to do that. And it's nice going into it knowing that we have this system where we have all of these various tests, and we're running them. Like, on every single commit, we go ahead and we run all of these, and it's really quick and easy to spot where we might have introduced regressions. I mean, it's not always possible because We don't do an infinite number of runs, and we might have an edge case that only happens like 1 out of every 50 times. But it's nice. Sometimes it catches stuff, which is a really obvious one on like CI. I mean, it wouldn't be obvious if you didn't look at the code really closely, knowing the failure, but it's there. And then just in general, knowing that we have this stuff running constantly will eventually trigger one of those cases. So, you know, all of this stuff, this came from inspiration from an awful lot of people. You know, number one probably on this in terms of what we're actually doing is Peter Alvaro. The original lineage-driven fault injection paper about a system called Molly is available there. There's also a talk, which I meant to put on here, but didn't, that he did at QCon London earlier in the year with Colton from Netflix about the work of how they were doing this at Netflix. It's a great talk because it's like, hey, we have this wonderful academic idea for Molly, but how you go about actually putting these into real systems, like that's the really interesting and difficult part. And I'm hoping that, you know, some people, if they see this and want to do it, can like use this talk as well to like get some kind of clue, because it took us quite a while to figure out how to do a lot of this stuff. It was really hard. Then there's another great talk of Peter's in general about testing his stuff around this. It's called Outwards from the Middle of the Maze. If you're not familiar with Kyle Kingsbury, I think he also gets called in like the bigger industry mags, like the man who tortures databases or whatnot. All of his Jepsen ones that are on his website are really great. The earlier ones are better because they have like lots of pictures of Barbie and stuff. But now that he's doing this for money, like they're a bit more toned down and calm and professional. But you know, they're still great for that. And if you want the non-professional side of him, you can follow him on Twitter, and there's plenty of non-professional there. Probably the first thing before even the lineage-driven fault injection that really got us started thinking about this, before we even started building it, was a talk this guy Will Wilson did. He was at Foundation DB before it got swallowed up into Apple, and he did a talk at Strangeloop called Testing Distributed Systems with Deterministic Failure Simulation, and it was really about how they went about building Foundation, and what they were doing was they actually built a database simulator before they built the database, and they came up with all of this stuff where they simulated everything that was going to happen, and they introduced faults like into the system, and they could do it in a deterministic fashion, so they could like set up a large number of machines, and they could, without them actually being like talking across nodes to each other on the network, they could still simulate network failures and everything. It's like really incredible talk. It's hugely inspirational. If you're interested in this stuff at all, you should definitely check it out. Katie, who's sitting right there, has a number of great talks about verification in distributed systems in general. I mean, there's a lot more that you can do beyond just like fault injection stuff and whatnot. There was a great ACMQ article that she did, and there's a talk version of it as well if you don't like reading, which is also a really good one. It was from QCon. Check both of those out. Inez, who works at Fastly now, you should, at the least, side thing, it's not in there, but you should follow her on Instagram because she has the cutest little dogs in there all the time. And she has a great talk called Testing in a Distributed World, which is another great overview of different possibilities for how you can go about doing this. There's the Chaos Engineering Group that was started by Netflix, and they have Principles of Chaos, which talks about the chaos engineering stuff that they do at Netflix, where they intentionally introduce failures into their production environment to see what happens. We don't have a production environment to do that in, and for us, anybody, we don't really want to go to a client and say, hey, by the way, can we mess with your production system? But you might be in an environment where it's like that, and I have to say at my previous job that I really very much enjoyed like going in at like 2 o'clock in the morning sometimes, and people hated me for this, but I would turn off random VMs just to see what would happen. It would always be really scary when you could turn off a VM and nobody would ask you until about 7 or 8 hours later what happened. You can learn an awful lot about your organization and your systems from doing that. So that's another like great resource to check out. If you want to, you can talk to me later, and I can tell you what we're doing with these wonderful little clusters of Raspberry Pis here, which are actually also part of our testing procedure. They're a lot of fun. They're kind of a pain in the ass to build. There's all these tiny little screws and all of these nice little like plastic things that make it look so cool. They have this thing to keep it from getting scratched where it's this like little paper film thing, and you have to, well, I don't know. Some people might be able to do this better, but it takes me about 45 minutes for each one. So it took me like, that's my cluster that I built, and it probably took me about 9 hours to put that together, and most of it was removing the piece of the paper off of the plastic thing, so it would have the proper aesthetic like appeal when it was sitting on my desk. A number of people helped me with this talk. Peter Alvaro gave me great feedback. Sylvan Kleb, she's the creator of the Pony programming language. He was really good on that. Zishan, awesome. John Mumm, Rob Rowland, and Andrew Turley, they all were really wonderful and helped me out with stuff. And that's it. Shanti Allen, thank you. And remember, the T, it's very important.
Questions?
Also, I'm really glad I cut about 25 slides out of this, because that would have been a problem. I've been practicing on not speaking like Chris Micklejohn from like 4 years ago. I did a version of this at QCon that was longer, and I finished it in 22 minutes. So, yeah.
Yeah, a question about the expected inputs, outputs matching up. Are they hand-curated input sets? Or?
Yes, that's currently what we're doing, is we're hand curating them. It's one of the things that we've thought about doing, is trying to come up with like something, but the thing that we came up with for that is the first thing you'd have to do on that then is that if you're going to have it randomly generate the stuff for you in some fashion, which is great, like basically property-based testing type stuff. With how we're doing all the rest of the fault injection would require us to rethink all of that, or re-implement all of the logic which we're supposed to be sticking in there. And at that point, like it's far less of a black box at that point, and we're really trying to stick more to the black box aspect of it. The thing that we're looking at much more before that, and we're getting ready to do now, is we did all of this on a file basis, which is wonderful for short test runs. But I mean, we're building a thing which is supposed to process hundreds of thousands or millions of things a second. If you want to test that this works correctly over 2 hours or 8 hours, or 8 hours, not possible in the size of stuff that you can get from Amazon. 2 hours, not possible in the size of stuff you can get from Amazon. We can do 30-minute runs, and it takes quite a while to actually get the results. So we've been putting most of our time into redoing it from being a file-based thing where our receiver actually is a system where itself is a streaming system. So if we run it for 8 hours and there was a failure 2 minutes in, if we're not actually going to run it for 8 hours, we're going to fail it after like those 2 minutes when we first see the failure.
Hello. So your fault injector was mostly about TCP. Did you also have injectors for transient problems like file system or underperforming CPUs or whatever?
Yeah, I mean, one of the big things that we do is we provide, resiliency for data that's stored in there. And our first version is one where we can survive the loss of a process, but not the loss of a machine, because we're writing stuff out to disk. So yeah, we are currently using this library which sits in between your application and POSIX, which we control from inside of ours in order to inject failures at the POSIX call level for file system operations. It's actually pretty damn cool. I can't think of the name of it at the moment because I'm not really working on that spot at the moment. We have like one person who's dedicated full-time just to figuring out ways to break stuff. And yeah, it's really kind of fun, and it took us about 2 weeks to figure out how to integrate it, but after that it was really easy. If I went through all the different ones that we were doing, then we'd still be here for another 2 hours. This TCP is a relatively easy one to explain what's going on there.
All right, so there will be coffee after this, so I suggest you just grab Sean T. Allen afterwards. Thank you.